Today we're going to be talking about exponents and looking at some properties of exponents. They are all listed there in your sheet. On my slide, some weird font things occurred, but I think these are all at the top of your notes. Memorizing properties is not something I really enjoy doing. It's not like a gift of mine. I'm not very good at memorizing formulas and stuff like that. So what I want to do is kind of look at why these properties are the way that they are. Yeah.
What are those things like?
It's a font bad thing. Like yours on your sheet are good. Problem.
I have the wrong note sheet too.
So what I want to do is look at why these properties are the way that they are. So the first one is the product property, and looking at the product property, what we're going to be doing is multiplying things that have the same base but possibly different exponents, possibly the same exponent, and looking at how we can combine those together into just one thing. What does x squared or x cubed mean?
X times x times x.
It's how many x's were multiplied together, right? So x squared is x and x. X cubed is x, x, x. So all together that is x to the fifth. How could I have gotten there without having to write out all the x's? Add the exponents. And that's what that first property tells us, is that when I have a product, when I'm multiplying the bases, I can add up the exponents. The second one has kind of this weird font thing going on, but it looks okay on your sheet. But the idea is that I have a power raised to another power. All right, well, x squared would be xx. And then cubing that means I'm going to do that 3 times. So how many x's do I have? 6. How could I have gotten there without having to write this all out?
There's multiply.
Multiply the exponents. So power to a power, we're going to multiply those exponents. The power of a product says if I have something that has a product on the inside with a power on the outside, well, xy squared would be like xy, xy. So if I try to clean that up and put all my x's together, I have x, what? Squared and y squared. So when you have a power on the outside, it says you have to give that power or apply that power to everything inside.
So the goal is like to get rid of the parentheses if there are.
Yep, the goal is to get rid of the parentheses if there are any parentheses and get it so that each variable only appears once in a problem.
Or simplified.
Simplified, yep. The property of negative exponent is easier explained after we look at the division property, as is the zero property. So we're going to jump down to the quotient property, which says I want to take, we'll say x to the fifth and divide it by x to the third. Well, x to the fifth is 5 x's. X to the third is 3 x's. And then what can I do? Cancel out some of them, which leaves 2 x's. How could I have gotten there without...
Subtract the 5.
I could just subtract them without having to write them all out. I can just subtract that. So when we multiply, our product property said we add them. When we divide, we're going to subtract them. Now when we go back and look at these two that we skipped here then, oops. If I have a negative exponent, so like x to the negative 2, it says that's the same thing as 1 over x squared. And let's think about why that might be. So if I had a problem that was like x cubed over x to the fifth, thinking about that division property, what would I do with those exponents? Subtract them. Top one minus bottom one, which would give me x to the negative 2. Okay, so just like in that blue one where we did our quotient and we subtracted 5 minus 3 gave us 2, in this one, smaller on the top, so 3 minus 5 gives us negative 2. But if I thought about actually writing it out and canceling them, 1, 2, 3 of them cancel, what am I left with? 1 over x squared. So a negative exponent is really an exponent that belongs in the denominator. Okay? In a simplified final answer, we would not consider a negative exponent to be simplified. So any negative exponents belong in the denominator.
Where did you get the x3 over 5?
Just as an example. Yep, so just to kind of compare it to what we did with the blue one. Yep. Yep, it reciprocates it or flips it. The zero property. Let's say I had something like x to the 5th over x to the 5th. According to the division rule, what would I do with those exponents? Subtract them, which would give me x to the 0. But x to the 5th over x to the 5th, what's anything divided by itself? 1. So that means an exponent of 0 gives an answer of 1. Anything to the 0 power is 1 except for 0 itself, which is kind of a weird thing. But otherwise, anything else to the 0 is equal to 1. In our last property there, the power of a quotient is really just the same as that power of a product rule, and it just says that when you have something in parentheses and the power is applied to the whole thing, you have to apply the power to each part of the thing. So we would give the power to the top and give the power to the bottom. So our rules for simplifying, when your directions say simplify, one of the hardest parts I find for students is knowing, like, when is it good enough? When am I done simplifying? Because sometimes what we consider simplified in math doesn't actually look simplified to students. So the rules, how you can know if you're done in the end, is you need to make sure that you only have one of each variable. If you've got x and then you've got another x somewhere else, that's not simplified. Okay? You should only have each variable appearing once. You should only have positive powers of variables. So if you have any negative exponents, we need to take care of those using that negative exponent property by flipping them over and putting them in the denominator. And you should have nothing to a 0 power, because anything to a 0 power is just equal to 1. So we would just want to take care of that as well. If those 3 things are satisfied, then your answer is simplified. Okay, so my examples also have weird font things going on. But this says 2 to the 3rd to the 4th. So we're applying that power to a power rule, and what do we do for power to a power? Multiply them. So I get 2 to the 12th. And that's good enough. You don't actually need to work out what 2 to the 12th is. I don't really care about you being able to type these things into your calculator. I care about you knowing and understanding these properties. Actually being able to calculate that isn't as big of a deal to me. Power to a power, we multiply those exponents. Oh boy, what is this one? 3/4 squared?
Yeah.
All right, so this one is that final property that a quotient is to a power. And what that property says is we have to give that power to everything inside. So we have to do a 3 squared over a 4 squared. And that's really fine if you just want to leave your answer right there. Otherwise, since these are numbers you probably already know, if you wanted to write it as 9/16, that's fine as well. But no decimals, please. Questions on that one?
How come we want to simplify that down? Wait, never mind.
It doesn't reduce down at all. If it did, you would want to do that. All right, this one is -5 to the 6th and -5 to the 4th. They are being multiplied together. They have the same base. The base is the bottom number there. So -5 is the base. And what do we do with the exponents?
You have different exponents.
Yeah, it's -4.
Oh, thanks. Okay. What do we do with the exponents?
Equals 0.
You add them.
We add them. So I get -5 to the 0, which is 1, because anything to the 0 power is equal to 1.
How come it wouldn't be negative?
-5 to the first is -5. Anything with a 0 exponent is equal to 1. Alright, this one says, do you have this one on yours? No? Okay.
To the negative fifth in parentheses and squared.
Alright, so we've got this power going on the outside. So our rule for a power outside is that we have to apply it to everything inside. So 2 squared and x to the -5 squared. Well, 2 squared you could either do or not do. I don't really care, but we'll just write it out as 4. You could leave it 2 squared if you wanted to. What do I do for x to the -5 squared? Power to a power, we multiply. So x to the -10, exponent to an exponent, we multiply. Now our rules for being simplified. Each letter should only show up once, so we're good with that. But we should have no negative exponent. So here I have a negative exponent. And our rule is that a negative exponent belongs in the denominator, but this negative exponent is in the denominator. And it's still negative. So what do you think we're going to do with it?
Add it.
We're going to flip it. We're going to flip it up to the top and make it an x to the +10. A negative exponent needs to go to the other part of the fraction. If it's on the top, it should go to the bottom of the fraction. If it's on the bottom, it should go to the top. And we only need to move the part that has the negative exponent. So the 4 stays where it is. It doesn't have any problems. It doesn't need to move. But that negative exponent needs to move. And negative exponents move to the part of the fraction that they are not in. Okay? So if it's on the bottom, it goes to the top.
How do you move it? Like, what's the justification for moving it?
It's that rule that says, it said a to a -m on the sheet is equal to a 1 over a to the m. So it's that property that says that we reciprocate or flip it over, which if it's already in the bottom, that would flip it to the top.
So if you had a negative on the top, and you flip it to the bottom.
Then you flip it to the bottom. Yep.
So anywhere when you have a negative, you automatically flip it.
Yep, if you have a negative exponent, you flip it. Alright, so the first thing I want to take care of here is this parentheses that's squared. What do I do when a whole group of something has a power?
Distribute it.
Kind of distribute it, give that power to everything inside of the group. So I get 7 squared. What do I do for b to the -3 squared? That's a power to a power, so what do I do with those? Multiply them. So I get b to the -6. And this other stuff will just tag along. Alright, well our rules for being simplified, we should only have one of each letter showing up, so we have way too many b's showing up in this problem. So we need to combine those. That 7 squared, you can make a 49, or you can leave a 7 squared. What do I do with all of those b's to combine them together? Add their exponents. What is the exponent on that very last one? 1. If there's no exponent written, it's the first. So if I add up all those exponents, I get b to the 0. What is b to the 0? 1. So this is like 49 times 1, or just 49. questions on that one? All right. All right, so first thing I want to take care of is those parentheses. When I have a squared happening outside of parentheses, we have to apply the squared to everything inside. So I get x squared and y to the fourth. Power to a power, you multiply. Then our rules for simplifying says that each letter should only show up once. So I've got 2 x's showing up and 2 y's showing up, so we need to combine them. This is a division problem. What does our rule say we do with exponents when we're dividing? Subtract them. So I get x to the -1. Do top exponent minus bottom exponent. And y to the, be careful, fifth. Top exponent minus bottom exponent. So 4 minus -1. Okay. Our division rule says we subtract exponents. So we do 2 minus 3, and that gives us the -1. And we do 4 minus -1, and that gives us 5. Okay, so our rules for simplifying says each letter should only show up once, so now we're good with that, but it also says we should not have any negative exponents. So I do have a negative exponent, and what do I do about that? Flip it to the bottom. We only flip the part that has a problem, so it's only the x that needs to flip to the bottom. And you could write x the first if you wanted. I wouldn't mark you off for that, or you could just write x. But that x has to flip down to the bottom because it has a negative. The y can stay on top because it doesn't have a problem. There is no real set order in which these properties need to be applied. So it's not like the order of operations that you have to do this one first, and then you have to do this property, and then you have to do this property. You can just kind of do whichever one makes the most sense to you. So in some of these problems, there was a different order that things could have been done that would result in the same answer, and that's fine. So that's something that can be a little bit overwhelming to students, and jumping into these problems when you get to your assignment is saying, like, I don't know where to start. Which property do I start with? And there isn't like a set rule on that. Okay? You can do whichever property kind of makes the most sense to you to apply first. All right, the next thing we're going to look at is something that you're probably already familiar with from a science class, which is scientific notation. Scientific notation is a way that we can write very, very large numbers or very, very small numbers instead of having to write a whole lot of zeros. So our first example says in 1997, Denmark had a population of this number and a gross domestic product, or GDP, of this number. Estimate the per capita. What does per capita mean?
Per person.
Per person GDP of Denmark. So that's an economic term. So if the country has this much money and there's this many people, kind of if it was split equally over them, then how much does each person have of that? So what are we asked for? We're asked for money per person. Okay? Money per people. These steps are kind of the problem-solving steps that I go through when I reach a word problem. I first want to think about, what is this question really asking me to do? If it's asking for the per person money, then it's money divided by people. Put both numbers into scientific notation. So the money would be 1.314 times 10 to the, and then we have to look at how many places we move that decimal over. So if I take that decimal from the end, I move back 3, 6, 9, 10, 11 places to get it up to be right behind the 1. And we're working in scientific notation, we just want one number in front of the decimal. And then the other number would be 5.284 times 10 to the, and look at how many places we move that one. 3, 6. Step 3 says divide the numbers, and by that I mean just the non-10 numbers. So I would grab a calculator and just divide those numbers that are in the front of the problem there. 1.314 divided by 5.284. And I get a not so nice number, but we'll just round that off to a couple places. Let's say it's 0.249. Same. Then divide the powers of 10 by using properties. So if we're dividing, what is our property? Subtract. So I would have 10 to the fifth. So I get 0.249 times 10 to the fifth. And then as our final answer, we want to write this in normal standard notation, so not scientific notation. So I want to take that decimal and I want to move it 5 places. 1, 2, 3, 4, 5. So I get 24900. Or just under 25,000 per person. Okay. And yes, you could find that same answer by just taking the original numbers and dividing them without doing any of the scientific notation stuff. But this is just put in this section to work with the powers of 10 as being properties there. An average adult has about this number of blood vessels in his feet of blood vessels in his or her body. How many times is greater is this than the circumference of the Earth, which is about 25,000 miles? And then it gives us a hint, so we need to do a conversion first. So thinking about what this question is asking us, it's asking us for blood vessels divided by the circumference of the Earth. We want to know how many times greater is it. So we're going to take it and divide it by the other one. We need to be comparing like things. We can't divide feet by miles. Right? So what we need to do is take that circumference of the Earth and multiply it by 5,280. And that'll turn it into feet. So then we've got our blood vessels. Divided by, when I did that multiplication, I got 132 with 6 zeros. Okay, so then if we're going to go through this same scientific notation, yes, we could just divide them just the way they are and like skip these steps. But the point is practicing with these properties of exponents and looking at how scientific notation works. So if we're going to turn this into scientific notation, we would go 5.28 times 10 to the what? 8. Divided by 1.32 times 10 to the 8th. Then we would divide our numbers. 5.28 divided by 1.32, and I get 4 times what? 10 to the 0, which is just 1, so we get 4. So that means if you took the blood vessels in the average human adult's body and you laid them end to end to end, you could wrap it around the equator 4 times. And all of that is in your body and working, ideally, perfectly if we are a healthy human adult. And each of them has a specific location it needs to be going and doing a certain task, which to me says, like, how do people think this happened by chance? Really? There's that much in our body, it goes around the equator 4 times and, like, oops, it's an accident? Like, no, there's got to be some sort of a design behind that, which means, to me, there has to be a designer behind that. Your homework is as listed on the bottom, all from section 6.1. There are some scientific notation problems, and then there's some other exponent property problems.